everyone. Welcome to Bioorganic Chemistry lecture. In this lecture, we will begin our understanding of carbohydrates, one of the most abundant and chemically fascinating classes of biomolecules. Although carbohydrates are widespread and very often discussed in the context of diet, our focus today will be their chemical structure, historical development, classification, and biological significance. By the end of this lecture, you should be able to define carbohydrates and classify them using both descriptive and chemical terminology. Secondly, understand how carbohydrate molecular structures are represented and recognize the interconversion in carbohydrates, including glycosidic linkages and projection transformation. Finally, understand chemical reactions and their biological significance. Therefore, before we move on to the topic, let's briefly review what type of background is expected. You should already be comfortable with chemical bonding, chirality, isomers, reactions of alcohols, aldehydes, and ketone. To a lesser extent, it's also good to have some knowledge about oxidation reduction reactions, enamine and ketoenol tautomerism, RS configuration, stability of various cyclic system, and optical rotation. However, we will revisit them as and when needed. So, why do carbohydrates deserve a detailed study? This is a question you might ask very often. First, they are among the most abundant organic components in living systems. Secondly, they are essential building blocks of all living organisms with very diverse structural and functional roles. And third, they perform numerous biological roles from energy storage to cell recognition and structural support. Therefore, we can confidently say that carbohydrates are not just fuel. They have multiple roles that are important to understand, where their chemical structure plays an important role in deciding how they can be utilized. Therefore, understanding the chemistry and the knowledge of chemical structure of carbohydrates will help us to get more insight on their different functions. Now, if you look at the carbohydrates, they have a very wide-ranging application beyond nutrition. In medicine, molecules such as streptomycin is a carbohydrate-based antibiotics. Heparin sulfate, shown here, is the most important molecule for blood clotting regulation. Chitin is a bio-based polymer. It's a polysaccharide, which is critical in many medical devices and tissue engineering. Almost everyone uses in cell lab gel electrophoresis, which is agarose gel. More recently, it's also emerging as an important component for tissue culture. Beyond food and energy, carbohydrates are almost in wood, paper, fabrics, DNA structure. The emerging nanocelluloses, cellulose nanocrystal, nanofibrillated celluloses, they are used in several innovative applications. So let us begin with our very familiar topic, that is carbohydrates and healthy diet. Carbohydrates are essential macronutrient, as all of you know and use it everyday life. However, they are not inherently bad. The key lies in choosing the healthier sources that support long-term wellness rather than relying on refined carbohydrates. The dietary perspective helps us to connect chemistry to real-world biological function. We can also look into some of the types of dietary carbohydrates. Sugars, which are naturally present in fruits, vegetable, dairy products. Examples include fructose, which is known as fruit sugar here, sucrose, as table sugar, and lactose, which is present in milk. Starch is found in many vegetables, grains, legumes, and provides sustained energy throughout complex glucose chain. And fibers, which are present again in fruits, vegetable, whole grains, and legumes, support digestive health and provides numerous health benefits. You may have noticed in many of the foods in the market labels like low carb or net carb, which appear these days in almost all refined products. Importantly, these terms are not regulated. That means there is no universal definition what is net carb and what is low carb. Typically, net carbs are calculated by subtracting the fiber or fiber and sugar alcohols from total carbohydrates. But the method varies. This suggests that how chemical definitions and marketing language don't always align, making chemical literacy especially important. This is the main reason why there is a need for understanding the chemical basis of their structure and function and biological significance. Most important for us than net carb and low carb is glycemic index. And then you can ask, what is glycemic index? The glycemic index is nothing but how carbohydrates are classified based on their potential to raise blood sugar levels. This classification system helps us to guide our dietary choices, particularly for weight management and metabolic health. So we can have the carbohydrate-based sources divided into high glycemic index foods and low glycemic index food. High GI food include potatoes, white bread, snacks, foods, refined ingredient, desserts containing refined flours. What they do is that they can cause a rapid spike in blood sugar level. Whereas low GI foods, such as whole grain, legumes, vegetables, and fruits, they produce slower or more controlled response. Once again, molecular structure influences this biological behavior that's seen, or the molecular structure affects how these biochemical processes are altered. Since each of these food sources contain different types of sugar, they have different way of responding. So now let us look into the historical perspective of carbohydrates and how the chemistry of carbohydrates was developed. The term carbohydrate derives from saccharides, which is a Greek word for sugar, and originally conceived as hydrates of carbon based on the very early chemical analysis. So the original concept by chemists was that if you take glucose as an example, here is a chemical formula. There are 6 carbon, 12 hydrogen, and 6 oxygen. Now we can rearrange this into as C6H2O6. That means we can consider this as an hydrates of carbon. These are 6 molecules of water and 6 carbon. Therefore, the carbohydrate term was originated, which unfortunately not true today. So this led to the general formula that all molecules they have CH2O will be carbohydrates. However, as the scientific understanding has advanced, scientists realized that this original formula had limitations and that requires some refinement. Why the limitations? Most of the carbohydrates follow this formula, but many fail. Some carbohydrates have additional elements such as nitrogen, phosphorus, and sulfur. Some non-carbohydrates are such as lactic acid shown here. This also has a same formula, but this is not a carbohydrate. This is a carboxylic acid, but it's not a carbohydrate. Therefore, there is a better definition is needed. And this is based on the work of several scientists. Some of the famous scientists who contributed developing the structural understanding, chemical composition, and writing their chemical structure and notations are Emil Fischer, Walter Haworth, and Louis Leloy. All of them got Nobel Prize for their contribution on various aspects of carbohydrate chemistry. Now, what is the modern definition of carbohydrates? The modern definition is based on two things. First, carbohydrates, if I take as an example of glucose, it has multiple hydroxyl groups. So that means there are more than two or more than two hydroxyl group. And they have a functional group. Here, this is a glucose, this is an aldehyde. And it is fructose, it has a ketone group. So these are polyhydroxy compounds which have some functional group, either aldehyde or ketose. Therefore, the definition is aldoses, those who have polyhydroxy aldehydes, and then ketoses, which are polyhydroxy ketones. Because they have multiple carbon center, they also have naturally the chiral center. So that means they have an asymmetric center. It means they often result in various isomers, which can be enantiomers, diastereomers, epimers. We will learn about this as we move along. Now, how to find a standardized way of writing the structure of carbohydrates? Many of you have seen this kind of two-dimensional notation developed by Emil Fischer, and this is known as Fischer projection. And here you will see the hydroxyl group. This is a simplified carbohydrate molecule. Example is a D-glyceraldehyde and L-Glyceraldehyde. It has two hydroxyl group. It also has two hydroxyl group. But what you notice is the arrangement of this hydroxyl group. And in this case, it is on the right side, it's on the left side. And this notation developed by Emil Fischer. How this structure was developed? The first is drawing convention. When you draw the structure of a carbohydrate, always the functional group, that is a carbonyl containing group, either aldehyde or ketone, will be as at the top or close to the top as possible. We will see in the example in the previous slide you saw fructose, where it was as close to the top as possible, whereas in glucose it was at the topmost carbon. Now, then, if the hydroxyl group at the bottommost asymmetric center, so the bottommost hydroxyl is here, but this is not an asymmetric center because it has two hydrogens, two groups of the same type. But the bottommost asymmetric center is here. And the hydroxyl group, when it is on the right side of the bottommost, then it is a D-glyceraldehyde. When the hydroxyl group at the bottommost asymmetric carbon towards the left side, then it is L-glyceraldehyde. So if you see D and L, the very simple way for looking at the structure is looking at the only hydroxyl group here. And if I have another, say, center here, the position of this do not decide whether it's D or L. Only the position of the hydroxyl group in the bottommost. You can write multiple carbon. We will look at this as we move along this lecture. Now, how historically Emil Fischer has assigned? He has assigned by accident that the D as also R. What does it mean? It means that it rotates in the clockwise direction, plane polarized right. If you have background in RS configuration, then you see that if you number the atom, they will move in this direction, the L will be in the opposite direction. So this was a pure accident, but later on it was turned out that D-glyceraldehyde is also R. However, it's important to note that R and S or D and L configuration describe only the three-dimensional arrangement of atoms around a chiral center. But it does not say the direction of optical rotation. For that, the symbols in modern days use plus and minus. Plus means retrorotatory, that rotates the plane polarized towards the right. Minus means levorotatory, that rotates the plane polarized right to the left. These properties are not predictable from structure alone. This must be measured using optical rotation using dedicated instrument. Now let us briefly look at the aldoses. We can classify carbohydrates many ways. One of the way is looking at the functional group. In this case, it's aldehyde, which is a CHO group, as shown here. Examples include glucose, ribose, galactose. And because these structures, when they are dissolved in water, they have some equilibrium with open chain structure. We will also learn it later. And they have free aldehyde. And because this aldehyde can undergo oxidation, they can reduce an oxidizing agent, then known as reducing sugar. I've shown previously that in the definition of carbohydrates, the functional group should be at the topmost or close to the top. This is an example. The topmost carbon is here, but this is the close to the topmost carbon. And example, fructose here, it is a polyhydroxyketone. So these are known as aldoses and ketoses. Now, we can also, this is based on structural difference, right? The main difference in the aldehyde and ketone is that we have an aldehyde group and a keto functional group. Second is the C1 carbon here. So if you label 1, 2, 3, 4, 5, 6, the aldehyde group is at C1, whereas if I label 2, 1, 2, the keto group is on carbon 2. That is one of the structural difference. Because the functional groups are different and located in different locations, this also affects their chemical reactivity. So they differ in their structure, aldoses and ketos. They also differ in their chemical reactivity. Because the structure affects the chemical reactivity, this also affects the biological roles, because that is important in metabolism and cellular processes. We will see these distinct roles when we move on to nucleic acids. Now, the other way of classifying the other than functional group is based on the number of carbon atoms. In this case, there are 3 carbon atoms, and this is based on the total number of carbon atoms in a given structure. So this becomes a triose. Because the functional group is here is aldehyde, we can call this aldo triose. Aldoses, but we can call it triose. And then is a tetrose. This has a 4 carbon. Pentoses, so 5 carbon sugar. Ribose, we will see this is an important sugar molecule when you go to nucleic acid. Hexoses, such as glucose, fructose, galactoses. So there are multiple ways of classifying carbohydrates. The first, and is specifically only on monosaccharides. And as we move on to the higher structure, we can classify them based on number of units. And here I show a cyclic structure, and we will come to that detail in the second part. And if you have 2 of those units linked together, then it's a disaccharides. If 3 or more than 3 to 10, then they are oligosaccharides. If more than 10, then that is a polysaccharide, this structure of a cellulose. So based on functional group, based on number of carbon, and based on number of units, so they can be classified into different categories. This classification is based on functional group or structure or number of units is also important because they affect directly their chemical reactivity and the metabolism and their biological roles and biochemical reaction. So this, as we go on, the complexity increases. As we move on to polysaccharide, you'll also see branched or only linear and very precisely branched and randomly branched structures. We will learn more about carbohydrates in detail in the coming lecture.